Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about the module Dirac's ket and bra notation for vectors under the paper Quantum Mechanics 1. So students, let us see what we are going to be learning in this module. Firstly, we'll get to know the properties of the ket and the bra vectors. So in that, we'll first define what is a ket vector, what is a bra vector, how the ket and the bra vectors are related to each other, and this will lead to some interesting observations, particularly if we are considering the same vector. Through this, we'll also learn the definition of the adjoint and the self-adjoint operators, and we'll see that self-adjoint operators are basically the operator A is equal to the operator A dragger, and this definition of the self-adjoint operator we'll see can be neatly derived in the following exposition. Then we'll also know the orthogonality theorem for eigenvectors of a self-adjoint operator. We'll learn the eigenvectors and the eigenvalues in the Dirac notation, and we'll see how these are defined. Followed by that, we'll also know the definition of the projection operator. And finally, we'll learn the representations of kets and bras. Now, as we have already discussed in the preceding modules, that what are the properties of linear vector spaces? Having done that, let us now turn over to study an elegant notation which was developed by Dirac to deal with vectors in the abstract vector space. So, we introduce the concept of the ket and the bra notations for the state vectors, and we shall see and discuss over here in the language that Dirac used the properties of the eigenvalues and the eigenvectors of a self-adjoint or Hermitian operator. We'll then discuss the concept of finite and infinite dimensional Hilbert space, develop the fundamental postulates of quantum mechanics, describe the representations of state vectors, and show how to express the matrix representation of state vectors and matrix elements of operators. Ket and bra vectors. Now we will be discussing the ket and bra vector notation. First of all, we define the scalar product, which has already been discussed earlier, as that if we have two vectors x and y, then the scalar product for these vectors is defined as scalar product of vector x and vector y is equal to the complex conjugate of the scalar product of vector y and vector x. And this relation is known to be linear with respect to y, which is the post factor, whereas it is antilinear with respect to x, which is the prefactor, and suggests that one can think of two vectors as belonging to two different spaces, linear in themselves, but related to each other antilinearly. So, if we look at this relation with respect to y, which is the post factor, and we say that with respect to y, this relation is linear, then we can actually think of three vectors, vector x, vector y, and vector z, and two scalars, alpha and beta, such that the scalar product of vector x and the product of alpha and vector y plus beta and vector z is equal to alpha times the scalar product of vector x and vector y plus beta times the scalar product of vector x and vector z. Similarly, the scalar product with respect to the prefactor, which is the vector x, is antilinear, and this can be defined as, supposing if we have three vectors, that is vectors x, y and z, and we have two scalars, that is alpha and beta, then the scalar product of alpha into x vector plus beta into y vector and the z vector is equal to alpha star times the scalar product of vector x and vector z plus beta star times the scalar product of vector y and vector z, where alpha star is the complex conjugate of the scalar alpha and beta star is the complex conjugate of the scalar beta. Now Dirac introduced the symbol psi ket. So the symbol that is given over here is called the ket, and psi ket is basically a ket vector to denote an abstract state vector, and this is called the ket vector in a complex vector space and a conjugate vector. Further, we can also define another vector which is called the ket psi bar and is given by the symbol that is shown over here in the equation and is called the bra vector. This is the complex conjugate state vector of the ket vector psi. Thus, the two spaces are not independent but dual to each other. Each relationship among the vectors in one space has its image in the other space. Relationship between ket and bra vectors. Thus, we can look at different vectors defined in the ket space and the bra space, where ket space are the state vectors and bra space is the conjugate state vector space. So, ket vector psi will have a conjugate state vector bra psi vector. Similarly, if there is an operator A in the ket space, it is transformed as operator A bar in the bra space. Also, in the ket space, operators act from left to right, while in the bra space, they act from right to left. So we can see this, that in case of ket space, if we have a scalar alpha, then the scalar alpha will act on the ket vector psi from the left, while in case of the conjugate space state vector space, if we have a vector bra vector psi, then alpha star, which is the complex conjugate of the scalar alpha, will act on the bra vector psi from the right. Also, if supposing we have three vectors xi, psi and phi, then in the ket space we can write the vector xi, ket vector xi, equal to ket vector psi plus ket vector phi, while in the bra space this will be bra vector phi plus bra vector psi is equal to bra vector xi, where we can see that the bra vectors for phi, psi and xi are the complex conjugates of the ket vectors for phi, psi and xi respectively. Again, if we have an operator A acting on a vector psi such that it defines another vector phi in the ket space, then we see that here the operator acts on the vector ket vector psi from the left as is shown in the equation, while in the bra space the operator is a bar and it acts on the state vector, that is the bra vector psi from the right. Further, we have these relations also which are defined for the ket and the bra space. So if we have two operators, now let us consider an example. So we can see that it is a simple exercise to verify that the operator d by dx, which is a differential operator, is not Hermitian, whereas the operator I d by dx is Hermitian in the space of square integrable functions. For the adjoint of the product of two operators, one finds that bra vector psi operator A into operator B acting on ket vector phi is equal to bra vector operator A dagger acting on psi operator B acting on ket vector phi is equal to bra vector operator B dagger operator A dagger acting on phi ket vector psi is equal to bra vector phi B, operator B dagger operator A dagger acting on ket vector phi the whole complex conjugate. From this equation one can see that if we have two operators A and B such that operator A into operator B hold dagger, then this is equal to operator B dagger into operator A dagger. Eigenvectors and eigenvalues in Dirac notation. Now let us see how using the Dirac notation we can write down the eigenvectors and their corresponding eigenvalues. So let us start with an operator A, which is a linear operator operating on a non-zero vector and has no effect other than changing the length of the vector while preserving its direction. That is, we have an operator A which when acting on the ket vector A is equal to A into the ket vector A, where A is in general a complex number and is called the eigenvalue of the operator A corresponding to the eigenvector ket vector A. And in general this A is complex. Then the eigenvalues of the self-adjoint operator are real. This is again something that we'll be studying, that when we find out the eigenvalues of self-adjoint operators, where the self-adjoint operators are defined as operator A is equal to the operator A dagger, and we'll show that how considering a set of eigenvectors, that is ket vector A, ket vector A prime, ket vector A double prime with the corresponding eigenvalues A prime, A double prime, such that operator A acting on ket vector A gives us the eigenvalue A into the ket vector A. Operator A acting on the ket vector A prime is equal to the eigenvalue A prime into the ket vector A prime. Operator A acting on ket vector A double prime is equal to the eigenvalue A double prime acting on the ket vector A double prime, and so on. orthogonality theorem. For a self-adjoint operator A, that is, operator A is equal to operator A dagger, we have the relation bra vector A prime operator A ket vector A is equal to bra vector A operator A ket vector A prime whole complex conjugate, which reduces to bra vector A prime ket vector A into A is equal to A prime bra vector A ket vector A prime whole star, and this is equal to A prime star bra vector A prime ket vector A, where the star denotes the complex conjugate. Further, we have that bra vector A prime ket vector A into within brackets A minus A prime star is equal to 0. Thus, if we take ket vector A is equal to ket vector A prime, it means since the norm bra vector A ket vector A is not equal to 0, this shows that every A is equal to A star, and eigenvalue of a self-adjoint operator is real since A star is the complex conjugate of A. So, if the eigenvalues, that is A and A star, are equal, then such eigenvalues for a self-adjoint operator are said to be real. Because eigenvalues can be real only if the eigenvalue is equal to the complex conjugate of itself. Also, from the equation, norm of A prime A into within brackets A minus A prime is equal to 0. It is clear that the scalar product becomes 0 when eigenvalues are different. These eigenvectors are then said to be orthogonal, that is, bra vector A prime ket vector A is equal to delta A prime A for normalized eigenvectors, where delta A prime A is equal to 1 if A prime is equal to A and is equal to 0 if A prime is not equal to A. Thus, eigenvalues of a Hermitian operator are 1 real and 2 corresponding to different eigenvalues are orthogonal. Projection operators. Now let us consider a self-adjoint operator A so that its eigenvectors form a complete set. It is then possible to write any state vector psi as ket vector psi is equal to summation over A lambda A into ket vector A, where lambda A is a scalar. Now, taking a scalar product of this equation with the ket vector A prime and using the orthonormality condition discussed earlier, we get bra vector A prime ket vector psi is equal to summation over A lambda A delta A prime A is equal to lambda A prime. On substituting it back, we get ket vector psi is equal to summation over A ket vector A bra vector A, ket vector psi. So from this equation we can define a quantity which is called the projection operator PA, such that the projection operator PA is equal to summation over A, ket vector A, bra vector A. And this projection vector, or rather projection operator, basically does the job of projecting the state ket vector psi on the state ket vector A. The sum of all the projection operators PA keeps the vector psi unchanged. This equation expresses the closure relation in its general form. Representation of kets and bras. In the ket vector A basis, the ket vector psi is represented by the set of its components. That is, we can write lambda A is equal to bra vector A, ket vector psi. These numbers can be arranged vertically to form a column matrix, where the column matrix is given as bra vector A, ket vector psi, bra vector A prime, ket vector psi, bra vector A double prime, ket vector psi, and so on. Similarly, for the representation of the bras in the ket vector A basis, we can write bra vector phi is equal to summation over A, bra vector phi, ket vector A, bra vector A, and the components bra vector phi, ket vector A are the complex conjugate of those of the ket vector phi and can be arranged horizontally to form the row matrix, which is given as bra vector phi, ket vector A, bra vector phi, ket vector A prime, bra vector phi, ket vector A double prime, and so on, and bra vector phi, ket vector AI. The product bra vector phi, ket vector psi is a matrix product with one column and one row and is therefore a number. Expression for matrix element. We can now extend our analysis of the bras and the kets to write in the matrix form the matrix element bra phi operator A ket psi in a given basis, say the ket vector ui basis, which is simply bra vector phi operator A ket vector psi is equal to bra vector phi projection operator A, again projection operator ket vector psi, and this is equal to summation over ij bra vector phi ket vector ui bra vector ui, which is the first projection operator in the above equation, operator A, then ket vector uj bra vector uj, which is the second projection operator in the above equation, and ket vector psi. And thus we finally have bra vector phi operator A ket vector psi is equal to summation over ij bi star aij cj, where bi star are the row matrix, aij is a square matrix, and cj is a column matrix, and this can be represented mathematically by the form of the equation given as bra vector phi operator A ket vector psi is equal to row matrix B1 star, B2 star, so on, Bi star and so on. Then square matrix A11, A12 and so on, A1i and so on, A21, A22 and so on, and A2i and so on. Then coming down to further rows, AI1, AI2 and so on, Aij and so on, and then going down further. And the column matrix C1, C2 and so on, Ci and so on. So students, now let us sum up what we have learned in this module. So firstly, we got to know about the properties of the ket and the bra vectors and how these vectors are defined. We also developed the entire formalism, quantum mechanical formalism based on the ket and the bra vectors, and we studied the various properties based on these notations. Then we learned the definition of adjoint and self-adjoint operators. And subsequent to knowing these definitions and the conditions because of which an adjoint operator is called a self-adjoint operator, we also understood that self-adjoint operators are Hermitian operators, where in case of these operators, the eigenvalues are real. Then we also got to know about the orthogonality theorem for eigenvectors of a self-adjoint operator. We learned about the eigenvectors and the eigenvalues in the Dirac notation, and we formulated the eigenvector and the eigenvalue equation under this notation. Then we also defined the projection operator and studied the properties of projection operator, and we realized that the projection operator is basically a kind of a mapping operator which maps one basis set of vectors onto another basis set of vectors. And after that, we learned the representations of the kets and the bras in the matrix form and saw how the ket and the bra vectors can be represented through a matrix representation. Thank you.